Greetings everyone, I am Abdullah Omar Galib and it's a pleasure to be here with you once again. I trust you all are. Am I audible? Sorry, am I audible? And okay, so, yeah. I trust you all are having a fantastic day, as Mr. Roger once said. Often, when you think you are at the end of something, you are at the beginning of something else. Our workshop today doesn't mark the conclusion of our quantum education. In fact, it's just the beginning of our exciting quantum adventure. During today's session, we will explore concepts like Bloss pair, a state vector, fundamental quantum gates, and some enjoyable experiments. Before we get into the exciting stuff, let's tackle a big question. What's quantum computing and how's it different from our regular computers? Think of your regular computer, the one you use for homework and gaming. It starts on something called bits, which are like tiny switches that can be either 1 or 0. Those bits team up to handle information and do maths. Now picture a quantum computer, something completely mind-blowing. Instead of bits, it uses quantum bits, or qubits we call it. Qubits are like magical switches that can do something astonishing. They can be both on or off at the same time. Same things, thanks to some crazy rules in quantum world, we call it superposition. But here's where it gets even cooler. Qubits can also be bodies in a special way called entanglement. When qubits are entangled, if you change the state of one, instantly it changes the state of another, no matters how apart they are from. It's like having a magical connection between them. Okay. Thanks to superposition and entanglement, quantum computers can tackle problems in a powerful way. Especially for a certain kind of challenges, they can solve tricky puzzles, simulate complex things like molecules for making new medicines, and even break codes way faster than our regular computers. In simple words, quantum computing is like having a superhero computer that can do some jobs way quicker and smarter than mm, the regular computer we use every day. It's like the difference between riding a regular bicycle and zooming through the sky with a rocket. Both are cool, but one can do things that another can only dream of. As we have seen, qubits are pretty mind binding. They are not just 0 and 1 like regular bits, and we have superposition phases and bunch of other extraordinary abilities peek into these tiny quantum switches. So representing qubit in a is a bit more like painting a masterpiece compared to the straightforward zeros and one of classical bits. But guess what? The quantum world has some pretty cool solution to this challenge. One of the coolest tool we have for understanding visualizing qubit is something called the Bloss pair. The thing you are watching here, the animation is a Bloss pair, but it's not the actual Bloss pair. So let's get into it. Bloss pair. Uh, so. mm we have already seen that qubits isn't just limited to the binary 0 and 1. It's more like quantum chameleon, able to take different states and perform some quantum acrobatics. To understand this, let's look at this Blosphere, it's like 3D map where there is three axes, x, y, and z. Imagine a cube. It helps to determine in which position the qubit belongs. Imagine if a qubit starts its journey along the x-axis. It means it's a pure state, but it's in a superposition state. We can be certain about its value. It's either 0 or 1, just like regular bit. But there's it gets exciting as we move the qubit away from the x-axis. Uh, uh, it starts to change its nature. It enters the realm of superposition, becomes a blend of superposition of either 1 or 0 or 1. So now let's spin our imagination further. If qubit takes role in y-axis, see here y-axis, it's just it doesn't just make it a superposition of 1 and 0. It adds a imaginary number I before the 1. So if it moves along y-axis there, then the phase of 1 becomes a positive y. If it goes the other direction, there is a negative y. So and for the when our qubit decide to venture along the z-axis, it's not in a superposition of 0 and 1 anymore. It instead it's all about phase. Its value might be 0 or 1, but with a twist or phase. We are going to discuss about z-axis further in this class later. So you see, Blosphere helps us visualize the incredible quantum journeys in a way that both mind bending and kind of beautiful. It's like a quantum canvas where qubits paint their unique stories, and we get to decode the quantum art. It's this fantastic tool that allows us to understand and work with the magic of quantum computing. Now let's learn how to code. This is the important part. How to code a Blosphere.
Excuse me,
Yes,
Abdullah.
yes.
I think there are a couple of people trying to join.
Oh, that
Yeah,
was.
sorry for interrupting.
No, it's okay. Thank you. Yes, if anyone have it, okay. Sorry. Thank you for. So let's learn how to code a Blosphere. So first we are going to use the Qiskit that we downloaded in our first class. So from Qiskit.visualization we are going to import plot blots multivector. It's a function that helps us to create a Blosphere and plot state q sphere. It is used for it's also a function that helps us to create q sphere. What is q sphere? I'm going to talk about it later. And visualize it, transition. It's also a function. It helps us to animate the Blosphere, but remember it only works for one qubit, not for the whole scenario. If it extends 2 qubit, or if you use measurement gate, then this function is not going to work. So after that we are going to import quantum circuit. It helps us to create a circuit full with quantum gates. And AER, it's a thing. AER helps us to get all the simulation that is at Qiskit live framework. And execute is also a function that helps us to get the result of the circuit that we are going to create. First, we are going to create a quantum circuit. So how do we create a quantum circuit? So we are going to add a variable qc, or if you want to give any name, you can give. I named it qc equal to quantum circuit, and this one value means that we are going to create a quantum circuit that has only one qubit. Then we are going to assign the backend. How we assign that? AER dot get backend helps us to get whatever whichever simulation we are going to use. For this case, we are going to use state vector simulator. Then we assign it to the backend. Now how do we get the result? So we are going to use a execute function, and where we are going to put our quantum circuit here and the backend here. So, and dot get result that helps us to get the result. So from here, state vector, how do we get the state, and what is a state vector? We are going to discuss this later. State vector equals to result dot get a state vector to the from qc. This code means we are getting the state vectors from the QC quantum circuit. So dot get state vector QC helps us to get all the state vector, and it saves the result in this variable. So when we plot it, plot plus pair multivector, and we assign the state vector here. See, it created a blosphere where the qubit is 0. We haven't put any gates yet, so that's why it's 0. So and also with the state vector, we can create a q spare. What is q spare? It's like how do I say, blosphere, but way more cooler, because it all not only give the idea of where it belongs, it also give us what phases it is at. So we haven't assigned any gate yet, that's why it's at 0 degree. So how do what is the parameters? We assign state vectors from here, then show a state phase equal to true. Yeah, and uses degree equal to true. That's why it giving the value in radian, sorry, degree mode. Otherwise the default mode is radian. So I suggest you to use radian, uh, radian angles, because it's more standard than the degree. So let's assign a gate for now. We are going to assign a gate qc dot ace. We are assigning a ace gate. So let's see how it so we are going to visualize how it changes the qubit. So we are going to play this loop. So yeah, this is how ace gate changes the phase of this qubit. So it creating a superposition of 0 and 1. So you have lots of question, because I haven't clear anything yet. Don't worry, I am going to explain everything in one by one. But first, let's understand what is state vector. So if you understand uh, what's Cartesian coordinates, you might be familiar with what's it's called, positions. So
Excuse me. I think another person is trying to join. I'm
okay,
sorry for interrupting.
no, it's okay. mm, Admit all. Hmm. So If you know what is Cartesian coordinates, you will understand what is state vector. So let's draw a. hmm. So this is x axis and this is y vectors. So vector basically means that something have both magnitude and its direction. So imagine a qubit's position is at here. Here is the drawing tool. Imagine a qubit's position is at here. So so what does that mean? Imagine y-axis is giving the information of probability of 0 qubit state 0. uh, and x is giving the information about 1 qubit state. So and this all the magnitudes here is giving the information about the square of the probability, square root of probability. So every unit here is the square root of probability. So um, what does this mean? So yeah, this mean that this mean yes, let me write. So it gives us some value. Imagine it's giving a, and this is the value b. So a square is the a square a square is the probability of getting the value 1, and b square is the probability of having the value uh, 2 sorry 0 b square. So we all know that having the if something if you know some experiment will if you do a experiment and you know that you will get 100% probability of getting something done, then the probability of that is 1. And if you know something is never going to happen, then the probability of that experiment is 0. So if we add up all the probabilities, we get a simple it will end up the resulting 1. So here a square is the probability of having the result 1, and b square is the having the result 0. So if we add up all the probabilities, a square plus b square, it will end up uh, adding, it will add up to sums up to 1. So can anyone tell me what is this equation? Does this equation look familiar? Can anyone tell me have you does this look familiar? Can you tell me what kind of what kind of equation it gives if you graph it and let's picture this equation. So we all know this equation of a circle is x square plus y square plus equal to r square, where r is the radius of a circle, right? So here a square plus b square is 1. What basically it basically means that it's giving us a circle where radius is 1. That's why we use blow sphere, a sphere to uh, allocate where this qubit is going to be. Like we cannot tell before measurement that this is going to be 0 or 1, but we can picture it that if it have some kind of probability of having 0 or 1, then we can picture it in a circle for now. So why spare? Because it for now we are using x and y axis, but I have mentioned that we not only use x and y axis, we also use z axis. So so basically x square plus y square and z square makes wait hmm, hmm. Makes a perfect what is called sphere. It also helps us to picture a you can say the position of I don't want to call it a position, but the you know if you want to picture something what will be the probability of a qubit to then a sphere is a better tool for it. So this is the state vector. Oh, state vector. So what is why the vector? So basically state vector is just the vector of the value a and b here. Let me draw it. Okay. So for now this circle we have two a and b. Yeah, so this what this vector gives us, it basically gives us an idea that the probability of square root of probability of qubit between 0 and 1. uh, this the list is actually called state vector, not it's not that fancy, but it helps. So we are if you study linear algebra, you have to calculate a state vector further in detail, but for now we are going to discuss about gates, because we need. Okay, so we are going to discuss about gate. So x gate. So mm So what is XGate? If you have studied computer science, then you might be familiar with XGate. It basically, in classical computer, it basically flips the state of a bit. It makes 0 1 and 1 to 0. But there's something difference between a quantum XGate and a classical XGate. So the In classical computing, there are x gate just flips regular bits from 0 to 1 or 1 to 0, but in quantum world the x gate does something pretty extraordinary. Imagine your qubit is somewhere on plus pair. When we apply the quantum x gate, it doesn't just flip the qubit like a pancake. It's more like a 180-degree somersault to the axis. This is where quantum magic happens. It transforms a bit in a way that classical qubit can flips, but it's rotate the x-axis, the position of the qubit to x-axis in a 180-degree. So that's the difference. So Xsketch, it's like our quantum flipper, but it's more acrobatic than the its classical computer. Let's see how to code a Xsketch. So we are going to import all the necessary thing like before, and we are going to create a quantum circuit where we give a value circuit equal to quantum circuit, where we are going to give quantum qubit 1 and classical qubit 1. So the first one should be the value of qubit, and the second one will determine how the number of classical bit. So then we will assign a gate. How do you assign a x gate? As the variable name dot the x actually give is um, how do I say x or any get you assign any gate after the variable name, some variable name dot the name of the gate you want to assign. For now we are assigning x gate to where to the first qubit. So first qubit, the index of first qubit is 0. This index of second qubit is 1. Like it starts from 0 and then goes on. That's why the index of the first qubit here is 0. So let's draw it, and circuit dot draw output is mpl. So this is we get. So what this picture mean, the q is telling us that it's a quantum circuit, and we apply x gate here. So and here one is one basically means that we have one classical bit here. So let's visualize it. So what happens when we apply x gate? So at first the qubit's position here is at 0. When we play it, see, it give a 180 degree flip to x-axis, and gave us the result 1. So if we apply so after the measurement, and we simulate, we get all the result, and when we see the plot histogram, we get the result 1. And the it's after running it for 1,000 time, it's just giving us the result 1. So there's no superposition here, it's just 100% 1. There's no 0 or any entanglement involved here. So let's add another x gate to this to a circuit. So we apply x gate twice and we get this circuit. So what's happening in this circuit? Let's try to understand. So so our initial qubit is 0. So when we 0, so when the 0 qubit goes through a X gate, it flips it makes it a qubit 1. 1. So this zero, X gate flips the state of the first qubit 0 to 1. Then when we apply 1 again to X gate, then it flips the 1 the qubit 1 to 0. So it's basically just returning the the first qubit result. So if it started with one qubit state, then it will flip the state and makes it 0, and then the 0, we apply 0 to the X gate again, and it will change its state and makes it once again. So it basically change makes the makes it how do I say? So it basically returns the initial qubit where we started from. If we started with one at the end, it will give us the one qubit. If we started it with 0, then it will at the end it will give us the state 0. So applying it's just applying identity matrix. So mm, basically applying to xget does nothing. So we visualize it. So at first we are going to at first xget to 0 state, and it flips it to 180 degree and it makes it 1. So again we apply xget, and it will flip it at 180 degree and it will give us the result 0. So basically it returns the first it rotates 360 degree and becomes the initial qubit it was. So after measuring it and getting plot histogram, we get the result 0 with 100% probability. So this is a homework for you. Here it this is the homework. So if you what happens if you apply xget to some superposition state, and I have wrote all the codes here. You can go through it and you can ask me questions in the Discord about this code if you find some difficulties. So uh, what is xget? So this is the interesting part of this session, because age gate creates a superposition. It is the age gate that creates superposition, and mm, like every qubit creates superposition, but rotation gates creates superposition, but age gate is special. It makes the Mm, uh, it makes a 50/50 probability of between 0 and 1. So yeah, let's go into let's dive into detail. So uh, states. So eh, the ace gate or Hadamard gate is like a magician once performing a mesmerizing trick with quantum bits and qubits or qubits. It's just makes it. regular in regular computer we know that the bit either can be 0 or 1, but when we apply ACE gate, it puts them in a superposition state, but like flipping a coin. When you flip a coin, you don't know what the result is going to be. So you have a 50-50 chance of getting head or tail. After getting the after measuring it, you get an answer, but before that you don't know what is going to happen. So ace gate helps us to create a superposition between 0 and 1. So it makes the 50-50 probability of getting 0 or 1. So when the out input of the ace gate was 0, it creates a superposition of 1 and 0. So we don't know what will be the result before measurement. So, and when the input of the edge gate was 1, it creates a superposition of minus 1 and 0. Here is the difference: minus 1 and 0. It's not 1 and 0. When the input was 0, it creates superposition of 1 and 0, and when it was 1, it creates a superposition of minus 1 and 0. So so basically the superposition and of 1 means the positive state, and the superposition of minus 1 and 0 makes it the negative state. So let's code the is get from before. We are going to import every necessary steps and functions we need. We are going to create a quantum circuit here. Then we are going to assign ace gate qc dot the name of the gate and the position here is 0, which basically means index 1. So when we visualize it, so let's say it makes flips the qubit to neither 0 or 1. It's just middle at the middle of 0 and 1. So it creates a probability of 50-50 that we don't have 0 and 1, but at the same time we have a I don't before it's like the measurement it's a flipping coin, but it's in a state before measurement. So yeah, then we measure it, and then when we apply it, we after running it for 1024, we get a 50% of 0 here and 50% of 1. So it basically means it creates a superposition state. So what happened so this we code it for when the initial qubit is 1. So we at first we create the same thing. We apply x gate at the top, and then we apply a gate here. When what does this mean? Let's dive. So here, first the initial qubit was 0. After applying the x gate, it turns the 0 state to 1, qubit state 1. So when the we learned that when the input of a ace gate is 1, the it makes it a superposition of minus 1 and 0. So it transforms the initial 0 qubit to a superposition of -1 and 0. So let's see in this code. So first we are applying x gate here. X gate basically making it to the give us the value 1. Then after applying the ACE gate, see, when we applied ACE gate from 0 state, the result was at here, and it was pointing out here. But after applying gate, first it becomes one state, and then it went the opposite direction. Opposite direction, opposite, which means that the there's a negative phase before 1, and the phase of 0 is positive. So after applying the measurement, we get a 50-50 of 0 and 1. So what if we apply ace case twice? So what why we are going so yeah, let's create a quantum circuit like this. I need everyone's uh, attention here, and I please turn on your mic because I'm going to ask question. So the initial qubit is 0, and after applying the ace gate, what we will get? Will we get? Hmm? So
0 is 50% and then 1 is 50%.
yes, 0 is 50% and 1 is 50%. So 1 and 0. So when we apply 1 to the ace gate, what will be the output? The output will be -1 and 0. And when we apply 0 to the ace gate again, the output will be 1 and 0. 1 or 0, sorry. So here the -1 and 1 cancels out each other, and finally we get the result 0. So applying ace gate twice is basically means you are applying a identity gate, which means that if the first state was 0, it will return the value 0, and if the first state was 1, it will return the value 1. So it basically does nothing. So let's see why. Oh, I have made an animation. Let's see why. So before this is the first ace gate. This is the result after the first ace gate. Applying we get a superposition of 1 and 0. After adding another ace gate, it rotates it and to the 0. See, the after applying the first ace gate, it makes it a superposition of 1 and 0, and after applying another ace gate, it flips it and makes it 0 again. So why did that happen? I made an animation. Please work. So yeah, so when we apply 0 to the ace gate, it becomes a superposition of 1 and 0, and the superpose one, when you apply 1 again, the so it becomes a superposition of -1 and 0, and the 0 becomes a superposition of 1 and 0. Then the -1 and 1 cancels out each other, and it we only get 0. So when we apply 1 at the beginning, it becomes a superposition of -1 and 0. Then when we apply -1 to the h gate, it becomes a superposition of, see the bracket here and this minus negative sign here, it makes it 1 and -0, and the 0 becomes a superposition of 1 and 0. So here the -0 and 0 cancels out each other, and we get only 1. Mm, so this is how we get. But what if we apply a measurement kit at the middle? So basically, when we measure a superposition state, it breaks the superposition state and makes it a normal state. So when what is happening here? Let's make it fresh. So when we apply 0 to this ace gate, it becomes a superposition of 1 and 0. After measuring it, it breaks the superposition state, and we get either 1 or 0. So we are not applying 0 and 1 to another ace gate simultaneously. That's why at the end we get a superposition state, not the actual state of the beginning. So at the middle, when we apply the ace gate, the measurement gate here, is it breaks the superposition, and we are not getting the initial state. So this is important, because it allow like measurement breaks the superposition state. That's why we are not getting the initial state. So if you want to have the superposition state, mm, want to have a superposition state, can you see my screen? Can you guys see my screen? So, sorry for the inconvenience. Sorry. So when we apply the measurement kit here, we are breaking the superposition state. So remember, if you want to get the initial value of something, don't apply measurement
Uh,
kit.
I think you're on mute.
Oh, oh, sorry, I don't know why that happened. So the measurement kit here breaks the superposition state. So when what it means, let's visualize it. So after applying 0 to the ace gate, it becomes a superposition of 0 and or 1. So after measuring the superposition state, we're getting either 1 or 0, not 0 superposition of 0 and 1. So after adding ace gate again, it gives us a superposition state, not an actual state. That's why if you want to it breaks the identity get identity, what's it's called, identity matrix, and basically we are getting a superposition state. That's why if you want to calculate the initial state before the age gate, you don't need to apply measurement gate at the end, middle. So that's you have to apply the measurement gate at the end, not at the middle. So this is so if you run this code again and again, you get a different state here. My laptop is slow. It will you will get a different values. Okay, I have to run it from the beginning. Let's see. Takes time. So if you run this code again and again, then it will give either positive state or negative state. Not an actual zero state, because we applied the measurement gate at the end. So the next we are going to talk about is coin flip experiment. So from the previous notebook, we have learned that the ace gate creates a superposition of uh, uh, 0 and 1. Do you know what else gives a superposition state 0 in resulting either 1 or 0? Yes. Okay. Can you guys join after this if it uh, ends after the class again? Okay. So also give me an give ping me at the Discord if it get close, because I can't see anything right now. So, can anyone tell that what makes this think it should see after running it again, it gives an super negative state result. Hmm? Mm, no, we can join at the same link after if it stop. Okay, so I'm closing it. Join this meeting with the same link. Okay. Okay. It's going to be a long class because the gates are not that easy. So should I start, or I should wait for other participants? Should I start? Wait. Hmm, okay. Should I start or wait? Wait. Hmm. Hmm. So am I audible and visible? Okay. So see, this is the code we ran. It was if we run it again, so it will give a different result each time. It will give different result each time, because after measuring it we are basically breaking the superposition state, and that's why it become either the, so after at the end we get a positive state or negative state. So yeah, we are going to talk about a experiment with a skate. So can anyone give me any example where there is two result and with 50-50 probability? Anyone besides the coin flip and that? A dicing roll gives a super position of 6 state, I think. So yeah, we have learned that ace gate creates a superposition of between 0 and 1. So and we know from coin, a coin also gives a superposition of head or tail. So we are going to create a code that gives us an experiment, the result that basically acts like a coin flip. So first we imported all the necessary file and created a quantum circuit. Then we assigned ace gate to this circuit. This is the name of the circuit, coin flip circuit. Then the name of the circuit dot the gate's name and the position of that gate. Then we measure it, and from measurement collect the result, and then we give if else statement. If we count 0 from that result, it will show this result, and else it will show this result. So let's run this code. Some taking time. Yeah, it's tail, and if we run it again, it's head. We run it again, it's tail. So basically it will give a random a random result, because we don't know if we are going to measure 0 or 1. So cx gate, so we learned that x gate flips the qubit. So mm, what is cx gate or control gate? So cx gate is made with two qubit. One is control qubit and another is target qubit. So if the qubit of the target qubit is 0, it does not the x gate does not act like x gate. So basically you see here that the this bit 0 is not flipping, 1 didn't flip. In this case, we see that when the control qubit is 1, the x gate is acting like a not gate. So 1 is turning into 0 and 0 is turning into 1. So what is mean, if the control gets the result 0, it tells the x gate act like the don't act like the x gate. So this x gate does not act like a x gate, and it does not flip the target qubit state. And when the control qubit is 1, then it tells the x gate to act like the x gate, and that's why we here we are getting the result 1, 0 to 1 or 1 to 0. So basically it's a conditional x gate. If the control qubit is 0, then it tells the x gate to don't act like x gate, and if the control qubit is 0, then it tells the x gate to act like a real x gate, and so it acts like the one. So here in this truth table, we see when the control qubit is 0, target qubit is 0, output is 0. It doesn't affect. So if the control qubit is 0, target qubit is 1, then it didn't change anything, so the output is 0 1. So but if the control qubit is 1, the target qubit is 0, it flips the target qubit and makes it 1 1. And if the control qubit is 1 and target qubit is 1, it changes the target qubit and makes it 1 0. So how do we code the CX gate? Control code. First we import all the necessary libraries from here, then we create a quantum circuit like that, but here we assign 2 qubit and 2 classical bit, because for to control qubit at least need 2 qubit to operate. So we apply the CX gate or gate, control not gate. How do we apply that? First we assign the name of the quantum circuit, then dot, then the name of the of this gate CX, and then we apply the value. The first value takes the position where the control qubit belongs, and the second one takes the value of the position of the target qubit. So then we measure it. This is the picture we are getting, and after the measurement we get the value 0 0, because the initial qubit was 0, the initial qubit of the control qubit was 0, so that's why it the x gate didn't act like the x gate. That's why the it didn't flip the 0 state here, so we are getting the value 0 0 here. So it's the same case where the control qubit was 1 and 0, and the target qubit is 1. So after applying it didn't flip the target qubit. That's why we are getting the result 0 and 1, 0 and 1 after measuring it. So uh, now we apply one state qubit to the control qubit here. So after, so let's visualize this. Okay, so after applying x gate, it becomes a control qubit becomes 1, and the target qubit is basically 0. So when the control qubit is 1, it passes through it and gives us the result 1, now when now the control qubit was is 1, that's why it will flip the target qubit 0 to uh, 0 to 1. So in this code, when we measure like before, we are getting the result 1 1, like I showed it here. So I gave a homework in this notebook. Do this of your own. If you face any problem, I am open at Discord. You can DM me or ping me at the Discord server, and I will discuss that there. And this is the most important circuit I am going to explain. And you have to it's important because if you um, it will help you to learn Bernstein-Wasserani algorithm in future, so pay attention. So in this before we see that target qubit didn't affect the control qubit. So whatever the state of the target qubit was, it didn't affect the control qubit. But the control qubit controlled the target qubit. But I mean, are you understanding it? Mm, Control qubit's job is to control the target qubit, and target qubit's job is to act they are the worker. Target qubits are like the worker, and control qubits are like the boss. But when we do apply when we apply edge gate like so, the target qubit changes the state of the control qubit. How? We are going to explain. So first we create a quantum circuit, then we apply x gate to the second qubit here like this. Then we apply h gate to both of these qubit, h gate at the first qubit and the second qubit. Then we apply control not gate here, and apply the h gate again. So let's visualize this. So the initial qubit was 0 of the control qubit, and the target qubit becomes 1 after the h gate. When we apply 0 to the h gate, it becomes an superposition of 1 0. And when we apply a one state qubit to h gate, it becomes a superposition of -1 0. This is where it gets tricky. So for when qubit 1 for all the qubit 1, it flips the state of the target qubit, and for the all the qubit 0, it does not flips the state of target qubit. So after applying it, it basically becomes a when we use linear algebra, mm, basically we have to do math here by linear algebra, but I have made an animation for you guys so that we don't have to touch linear algebra, but I prefer linear algebra here. So basically after the every qubit changes its position. After simplifying it, we get a superposition of -1 0 and -1 0. After applying it, it becomes 1 1. Here you see, have you noticed that for the for we have you noticed that uh, when the qubit here is 1 and the target control qubit was 0, so but after applying ace gate at both side, we get the result here 1 and 0. What does that mean? Basically, this target qubit changed the position, the state of the control qubit, like the worker is controlling the boss here because of this this edge gate. That's why this is why it's so important, and we are going to discuss about it furthermore in Bernstein-Vasarely algorithm, which will be conducted tomorrow. I think it's not at today's class schedule. So, if you have any question about this, you can ask, because it's a really tricky one, and I hope everyone should ask question about this, because we need to understand this clearly to learn Bernstein-Vasarely algorithm. If you understand this animation I made, you will it basically gives an idea how the target qubit is controlling the control qubit here. So, mm, do I need to explain it again? Okay, I will teach this because it's really important. So, okay, so when the control qubit is 0, target qubit is 1. After applying it, we get the superposition of 0 and 1, and superposition of -1 and 0 and 0. So for every 0 qubit, we it changes the these qubits, and for it does not change the target qubit, and for every one qubit state 1, it changes the target qubit. So, so because of this negative one, it also affects the state of the control qubit. So we have to do linear algebra for that, but I am not entering there because it might be tricky for high school student. So it changes the state of 0 and -1 because of this -1. So after applying -1 and 0, superposition state of -1 and 0 to ace gate, it becomes the output becomes 1, as we learned from 1, and it becomes the same here. Control C. Okay. When the input of the edge gate is superposition of -1, we learned that it returns the value 1. So after here we can see the control qubit was 0, but the output of the control qubit is now 1, and the initial state of the target qubit was 1, and the output of the target qubit is 1. So basically the target qubit didn't change here, but the control qubit changed is state. So here the target qubit controlled the control qubit, like worker controlled the riot against the boss. So we are going so if anyone don't have any question, then we will move to rotation gate. So what is rotation gate? So from Blosphere notebook we have learned that we use Blosphere to define the position of the qubit state. So rotation gate helps us to, how much rotation a qubit should take. So in each gate we cannot define how much we are going to control it. It's basically going to be zero. It gives us the 50-50 probability of 0 1 1. But what if we want something else, like we want this measurement to be the probability of the this qubit should be greater than the other qubit, then how will we assign that? For that we use a rotation gate. So we have already learned that there are three axes here, x, y and z. So for every axis we have a separate rotation gate, which are rotation x gate, rotation y gate and rotation z gate. So how do we assign that? First we import all the necessary the all the necessary live functions from cascade. Then we are taking pi from value pi from math, so that we can assign the angle what angle should it take. Then first we create a wait create a quantum circuit. it, we just made an empty plus pair here. Now how to assign it? So at first we give the name of the quantum circuit dot the name of the gate we want to apply, which is um, rotation y gate ry. So we want let's see what happens. We apply rotation gate to this qubit. We want to rotate this arrow 90-degree around the y axis. So we apply pi by 2, which means 90-degree in degree mode, and this value indicates the position of the gate. So if it is 0, then it will the rotation y gate will stay at the first qubit. If it was 1, then the rotation y qubit would be at the second qubit. So after drawing it we see the result, and let's see how it goes. So after applying rotation y gate 90 with 90-degree value, we see the result like this. So it rotated 90-degree alongside the y axis and gave us the value this. It moved like that. And what if we want to we want to rotate the qubit 60-degree around the x-axis? So for that we created a quantum circuit here. Then assign the rotation y x gate, and we simply entered the how much rotation it should take. For 60-degree we assign pi by 3, which means 60-degree in radian mode. And this is the position where the x gate should be. So after applying that we get this, and see what happens. So it rotates the arrow to 60 degree alongside the x-axis. So it goes same for the z-axis. So y gate y-gate is different. We learned that there in classical computer we have x-gate, but what is y-gate? Pauli y-gate. So in xgate we saw that it makes 0 to 1 and makes the 1 bit to 0 bit. But in y gate when we apply y gate, it not just changes the value, it also add a phase. So when we apply y gate to 0, it becomes the output is I I1. I is the imaginary number, and determining its phase, and one it flips the, like it's acting. It not only flipped the result, it also add a phase, and also when we applied one, it flipped it makes it 0 and also added minus I to in front of the 0 state. So it what it actually what it did is uh, it rotates the input around the x-axis of the block sphere by 180 degree. So how do we assign that in code? First we import all the necessary libraries, then create a quantum circuit, and then we apply the y-gate. Basically QC is the name of the quantum circuit we created, and the dot the name of the circuit, the name of the gate, the name of the gate is y, and 0 is the position. So yeah, when you draw it, we see the gate here. So what it did, it flipped it, yeah, alongside it flip it 180 degree alongside the y-axis. That's why we get when we apply it, it becomes 0 becomes 1, and it at a phase I, and when we it start from 1, it makes it 0 and apply is a phase minus 1, minus I, sorry, it's a imagine number. So for the when the state is 1, when the initial state was 1, after applying a y gate to it, we get the result 0, but it moved as it move alongside with the y-axis. That's why it gave a phase minus I in front of the sorry, minus I in front of the state 0, yeah, like this. And this is the z gate. I'm going I'm speed running now. So z gate is basically it flips do the same thing like y gate, but in z axis. So when we apply z gate to 0 state, it makes it doesn't change the state of um, mm, the output, but when we apply 1 to the zgate, it makes the output minus 1. So when we apply zgate to the 0 qubit, it should not change, yeah, it didn't change. And if we add 1 to the for 1 to 1, then it not only it first the x gate made it 1, and the z gate when we do a 180 degree rotation alongside the z gate, in the when the initial qubit was 1, it made the output -1 because mm, uh, uh, the when it was 1, if we rotate it alongside the z-axis, it shows the up, how do I say, uh, spin, if we should we call it spin, like, if the qubit state in is in 0, the z gate leaves it unchanged. It does not change because it how do I say, if you rotate it 180 degree in positive direction, then it should not change any phase, or but if you rotate it alongside the z-axis 180 degree at the negative direction, it should give a negative value. That's why when the qubit is in one state, the z gate adds a phase minus in front of the 1. So this is the z gate. And tomorrow I will teach you Bell state algorithm, Bernstein-Verzerani algorithm, and teleportation, and how to use a real life quantum computer in detail. Not too much detail, but yeah, I will teach you. And after this class I will give all the assignments. Please, if complete that assignment if you want to have uh, certificate on excellency. So yeah, this is today's class. If you have any question, please raise your hand, and we will discuss about that. And if you if you want, do you if you have any questions right now, but while you face any problems, please ping me at the discord, and I will. Okay. Yes, you can.
When are the assignments due?
After this class I have made the assignment, so after this class I will uh, publish the assignment. Mm. So and if you go through that notebook and read them, if you have any question, not right now, but while reading the notebooks, you can always ask me at the discord. I'll be there. So yeah, this is today's class. Hope you enjoyed. Do you have any question? Uh, mm, any question about gates or anything? How to how that code works, or any specific question? Okay. Okay. So yeah, and that's all, folks. See you tomorrow, or okay, see you tomorrow. Bye. Yeah, thank you.
Have a good day.
Thank you.